Good evening, everyone. Good evening, friends. Welcome back to our session on RNN recurrent neural networks. So, in the previous sessions, we have understood the concept of RNN, right? So, in this today's session, we are going to understand a use case, okay, where we'll be predicting the stock price of Google using RNN as well as LSTM, long short-term memory, right? So, friends, if you're joining for the first time, do consider subscribing our channel as well because we are going to come up with amazing content in the upcoming programs. So I request everyone to subscribe to our channel. Right. So before we start the use case, let us quickly go through the data that we have. See here. So there are in total 6 columns in which we have the data recorded in the sequence of time. Right? If you see, each and every row has a sequence. We are aware that RNN and the types of RNN work well for sequential data. So this data that we are going to work on is time series data. Okay. So the data is recorded with respect to time. It's nothing but date. Okay. So on a specific day, what is the price of Google stock is what we have the information over here. I hope it's making sense. Now we'll also understand what does it mean by open, high, low, close, and volume. Okay, so you take any one specific day, all the days have all the 5 values. Okay, you take any one specific day, it has all the 5 values: open value, high, low, close, and volume. What are these representing? Okay, so whenever you are working on any use case, ensure that you also be clear on the features. Okay, you should be understanding the features. So here, open represents stock of one Google, one stock price uh, at the beginning of that particular day. So on this day, so the stock price of Google is this much at the starting of the day. In the same way, the close price is this much. Okay, so everything we have it probably in the value of dollars. So at the end of the day, on 3rd of Jan 2012 is $663. So this is the closing price of Google stock, one single stock. Then, what is this high and low? High and low is also representing the price. Okay, so the price of one stock, what is the high value and the low value? Okay, and the volume represents the number of stocks that got traded on that specific day. So in this process, we are going to take the 2 columns. One is date, and we'll be taking open column. Okay, so we are going to forecast the open column prices. So on the given day, what will be the price of one Google stock, okay, at the opening of the specific day is what we are going to predict. So I hope it's making sense. We have collected the data and probably there are around 1200 rows. Okay, so I hope the context is very clear. Now let's get started, friends. Right. So again, before we start the class, friends, if you are directly joining the use case, probably you may not understand, the architecture of RNN, how RNN works and all. Right? So go and cover the sessions that we have done with respect to recurrent neural networks. Okay, we have understood why ANN and CNN cannot be used for sequential data. Then we have also understood the introduction part to RNN, then architecture of RNN, and also the types of RNN, and finally the working principle of RNN in the previous sessions. So just go through these sessions, then listen to this particular session. right? So the first step is to import the required libraries. Whatever the libraries that are required, we are supposed to import them. So I'm importing OS library as usual. In order to give permissions to the operating system, we import OS library. Then we are also importing NumPy module, and I'm giving an alias name as NP. So NumPy, it is used for handling arrays. So in order to do basic mathematical calculations, we use NumPy. Then I'm also importing pandas for data manipulation, giving an alias name as PD. Okay. Then followed by importing pyplot module from matplotlib. Okay, this is used for visualizations. Okay, giving an alias name as PLT and Cborn as SNS. Even Cborn is a library which is used for data manipulation, data visualization. Then followed by sklearn.preprocessing. From preprocessing module, I'm just importing min-max scalar for scaling the features. Okay, in order to bring the features to a particular scale, I'm importing min-max scalar. Then from keras.models, I'm importing sequential. So this sequential helps us to, group a linear stack of layers into a model. Okay, we'll have a stack of layers and that can be made as a model. And from keras.layers, I'm importing dense to create, the layers, dense layers. Then I'm also importing simple RNN. Okay, so this is going to give me a fully connected RNN network. Then dropout. So we are aware that dropout is a regularization technique that helps us to drop randomly, some of the random neurons, and LSTM to build an LSTM model. And finally, from sklearn.metrics, I'm importing mean squared error, MSE. So this will be my evaluation metric. So all these libraries I'm importing in a single go. Done. Then I have the data in a CSV file. Okay. Ensure that you load the data into the files. Okay. So copy the path and use the same path in your function, that is read underscore CSV. So once after executing this line of code, the data gets loaded into the Python's memory and it will be stored in this variable. Okay, so data is stored in the data variable. Done. So in order to have a look on my data, I'm using head function to return the top records. By default, head function will return 5 records. Yes, we are aware of head function, right? So even though if you don't pass any value in the head function, it returns default 5 rows, the top 5 rows, right? So let me execute. So these are the 5 rows. What is the purpose of using head function? If that is your question, in order to have a quick glance on your data, we use head function so that at least you'll have a look on the top 5 rows. Instead of look, if there are millions of records, we cannot go and have a look on all the millions of records. Am I right? So if you just have a look at the top 5 to 10 rows, that is more than enough. So that is the purpose of head function. Then I'm also using info function. Info function helps us to give the information about the data set. Okay, so where we get the number of rows, the index for the rows, followed by number of columns, then the column names, column index, and the non-null count, as well as the data type associated with each column. So this will be the output for info function, and I can clearly see that there are 1258 rows where the index of these rows is from 0 to 1257, and all the columns, in all the columns, I don't see any kind of null values, and there are total 6 columns. Okay, so the count is 1258. And if you observe, 3 columns have the data type as float, and rest of the columns have the data type as object, right? Yes. Now, on this data set, I'm performing describe function. Describe function is going to give us the descriptive statistics. Okay, so it will return as the count, mean, standard deviation, minimum, maximum, Q1, Q2, and Q3. Right? So if you see here, did it return us the descriptive statistics for all the columns? No. It has returned us the output for only 3 columns. It is for open column, then high and low columns only. Why not for rest of the columns? Might be a question, right? So that is just because, only these 3 columns are numeric. Rest of the columns are non-numeric. Object represents they are categorical. But anyhow, we know that close and volume are not categorical, but they are stored in object data type. We are supposed to do typecasting, but anyhow, I don't want to worry about the rest of the columns. My area of interest is just open the column, open column. I want to predict the prices that are available in the open column only, right? Yes. I can clearly see that the data is, it's not scaled. How come? The minimum value is 279 in the open column, as well as the maximum value is 816. So it seems that it's not in a particular scale. Okay. And let us do that scaling as well. Right. Now, I'll take the open column alone. Okay. So when you say data, square braces of any column, it returns a data frame. Right. So what I'm trying to do is I'm going to extract the values that are present in open column, okay, and store them separately. So dot values is going to return the values from the open column, and it will return an array. So let me execute, and I'm storing it in stock prices. So when you say stock prices, you're getting the values that are available in the open column, but this is an array. It's an array, right? Then I'm splitting the data set into train and test. Okay, so this is the only column that I'm interested in, right? Because I'm supposed to forecast the price of one Google stock, okay, at the starting of the day. It's nothing but the open column, the values that we have in the open column. So I have separated the open column from the entire data set. Now, I'm going to, split this open column into train and test. How? So I'll take the entire values. So length of stock prices will return me the length of this array. We are aware that it's 1258. Okay. So minus 50 will return me 1208. Am I right? Yes. So that will be the size of train size. That will be the size of train underscore size. Then I'm using this number to split my data. So stock underscore prices is nothing but the array. So on this array, I am performing, what is this? What is this called? Slicing. So colon train underscore size is 1208. So it's nothing but 0 colon 1208. So the first 1208 values will be part of the train data set. Then followed by the next 50 values will be part of the test data set. So for better understanding, I'm printing train and test shape. You should get 1208, 1 and 50, 1. I hope it's clear. Then on the train data set, I'm going to perform min-max scaling. So min-max scaling is a feature scaling technique which helps us to, you know, perform. It's going to bring all the values between a range. So what I'm trying to do is I'll take the values that are present inside this train data, okay, and I'll get them to a range of 0 to 1. So I'm initializing the scalar, and this scalar I'll be applying on the train data. So this will be fitted and the transformed results will be obtained and stored in train underscore scaled. So let me print train underscore scaled values. So here you observe all the values will be only between 0 and 1. So please tell me the formula for min-max scaling, friends. What will be the formula for min-max scaling? X minus min by max minus min. Am I right? Yes. So that formula will be used. X minus minimum value by maximum value minus minimum value will be used, and you'll get the values. These values will be written as output. Now, I take all these values and I would like to plot a graph, just a normal graph. So plot function is present inside the pyplot, plt dot plot of train underscore scale, which is nothing but the values that we have got. The scaled values of the train data is what we are going to plot, and the title should be normalized training data, and we are going to visualize it with show function. So here are the index, and on the y-axis we have the values. On x-axis we have the index. So in train data, there are 1208 records. So from 0 to 1207 is what you'll see. Okay. Then the values are just between 0 to 1 because they are scaled. Now, I'm also preparing my training data set with timestamps because in RNN, timestamps is what it's mandatory, right? Because it uses the output of the previous timestamps as part of the memory component. I'm taking timestamps as 50. Okay. Then I'm defining two empty list. Then I'm coming up with a for loop. Okay. Where I'm using this timestamps and the length of train underscore scale, which is nothing but 1208, comma 1. Okay. So that becomes the length of the array because this is an array, friends. Okay. So what I'm doing here is I'm just using this for loop to prepare my training data set. Okay, once this data set got appended to this list, those lists will be converted to arrays again. And once the arrays are obtained, we are going to reshape them to form X train. So we are going to get X train here. See, now I'll define my RNN architecture. Very simple. It's not complicated like CNN. It's very simple. So I'll be using sequential method, okay, which is going to help us to have stack of layers one by one. So the first layer that I'm going to add is simple RNN. So we are going to build an RNN model, right? So we'll use simple RNN function in which initially we have 50 neurons, okay, where the activation function is tan h. Tan h help us to have the output between -1 to +1, and returns underscore sequences is equals to 2 represents. That means the previous case, you know, whatever the output that is returned from the previous sequences will be used for the next layer is what it represents. And input shape, you get it from the X string. Okay, so in this way, you are going to build your first layer of RNN. Then followed by the dropout layer. So as part of the dropout, I'm keeping that 0.2 represent 20% of the neurons will be dropped randomly, friends. Okay, so this ensures that not every time the same neurons have to learn as part of the learning journey. Okay, so when randomly 20% of the neurons get dropped, if they are removed, you know, it ensures that each and every neuron, as part of this training journey, will learn the patterns. This is a regularization technique which helps us to prevent overfitting. Okay, so dropout is mandatory. Then I'll also add one more layer using simple RNN where I'll keep the number of neurons as 50, activation function as stan_h, and returns underscore sequences as true. The same, I'm repeating. Okay, again, the dropout value is 20%. Is it same again? Yes. So I just have repeated 3 layers. But in the last layer, okay, so I have just defined the simple layer with 50 neurons. Okay, and I did not kept return underscore sequences. I did not define. So it takes by default the value will be false, and the previous sequences will not be used under the calculations. Then the dropout is again same 20%, and in the final layer as part of the output layer you'll have only one neuron, and that is created using dense function, and this makes the entire architecture of RNN, the basic RNN. So this model, in order to get compiled, back propagated, you should have used some optimizer. I'm using Adam, friends. I'm using Adam, and the loss will be calculated using MSE, mean squared error. Mean squared error is being captured as part of the training journey, and in order to get the output table, we use summary function. This is going to give me a table with layers followed by neurons, the output layers, then the parameters. See, so the layer followed by the shape, output shape, then the parameters. Simple. Now, once after defining your architecture for the model, you're supposed to use that model to fit on the training data. So I'm passing X train and the Y train, okay, of size both 1158, okay, and the epochs that I'm coming up with is 100. What is an epoch? Epoch is nothing but, when you pass your entire data once, that becomes an epoch. So one forward propagation and backward propagation together represents an epoch. And per each batch, only 32 records is what it takes. So I'm executing. So now all 100 epochs will get started. Don't get worried. It does not take long time because this is not unstructured data, right? So probably you may have get, CNN into the picture where it took 1 hour for execution. But this takes very less time. Within probably 1-2 minutes, we'll complete off all the 100 epochs. So it is giving the epoch number and the number of batches in each and every epoch, and what is the time that has consumed per epoch. Okay, what is the time that was consumed per step, and the loss is also being calculated, friends. If you observe, see how the loss is gradually decreasing as the number of epochs is increasing. the loss is decreasing. What is the loss initially? It is, oh my God, initially it is 0.3. That means around 40%. But now slowly it has reduced. It's around 0.6%. Let's wait for a couple of minutes. It's executing. It will complete all the 100 epochs probably in the next 1-2 minutes. No worries. Right. You see how fast it is? It just completed all the 100 epochs in 3 minutes 46 seconds. This is just because of the data, friends. Since I'm working on structured data, it's taking very less time, right? But if you see, as the number of epochs got increased, I can clearly see the loss got decreased. It's 0.2 percentage. Probably seems like overfitted, right? Now, let me also get the predictions. Our model is ready. Okay, so I'll prepare my test data set for getting the predictions using the same process. Okay, then I'll use the model that has built. Okay, and I'll predict on the test data. Okay, and I'll get the predictions. So these predictions again, since we have performed min-max scaling, they'll be between 0 to 1. So I will perform inverse underscore transform. So this will help us to get the original values. Okay, so this will undo the scaling part and you'll get the original values. And those are stored under predicted RNN, right? So what I'm going to do is, since I have actual and also I have predicted values, I'm going to get, I'm going to plot to see how the predictions are. Okay, I'm comparing the predictions and the actual. So the color of the actual will be in red in color and the predicted values will be in blue in color. So the label is also given over here. So for the actual values, we'll keep it as real Google stock price. And for the blue colored line, it is predicted Google stock price by RNN. The title of the plot should be like Google stock price prediction using RNN and X label. For X-axis, the label should be time, And for the y-axis, the label should be stock price. And I would like to have a legend of these, and I would like to visualize the plot. See, so this is how we get the predictions. So these are our actual red color line is representing our actual stock prices of Google, and you know the blue line is representing our predictions. Seems like the predictions are not close to, they're not close to the original values. No, probably here, yes. In some cases, yes, but in majority of the cases, no. So for that reason, we are also coming up with the LSTM model. So this LSTM model, let's see how LSTM model is going to, give the output on the same data. Anyhow, the vanilla RNN model did not perform well. Now I'll prepare the data for LSTM. Then I'm just applying the reshape. Whatever the data that I have, the train data, I'm applying the reshape. I'll get the train data ready. So before I pass the train data on the model, I should build my LSTM model architecture. For that, I'm going to use sequential function. So this will help us to group a linear stack of layers into a model. So I'll start adding the layers. Under LSTM, so I'll use LSTM where I have 10 neurons. The input shape is again the same. Okay, the time steps is 50. Okay, and in the dense, using the dense function as part of the output layer, I'll keep only one neuron. Okay, so this marks my, this is just a simple LSTM model architecture that I'm coming up with, and I'll use compile function where the loss will be calculated using MSC, and the optimizer that I'm going to use is Atom. And I'm also using a summary function to have a look on that table. See, so it gave me, the layers and the shape of the outputs at each and every layer and the parameters. Now, the same pattern. Once after the architecture got ready, I'll use the model, I'll fit it on the train data, and I'll pass the epochs, and the batch size is just only one. Okay, so one record at a time. That's what it means. So again, let us undergo the training journey. Even this 50 epochs also, it does not take much time, friends. Just hold on for 1-2 minutes, because I want to compare the results of RNN and LSTM at the end. You see how the loss is getting reduced as the number of epochs is getting increased. It is giving the time that is taken by the model for each and every epoch. This represents the epochs. First epoch of 50, second epoch of 50. Then down to it you have again two numbers, right? This represents the batch size. So these many batches, 1158 are the number of batches, and all of them have been completed. That's what it means. Are we done? Yes. So we are done with the 50 epochs. Now I'll use this model that got trained, the LSTM model, long short-term memory, long short-term memory model. So I'll be using it on the test data to get the predictions. So for that, I'm preparing my test data where I'm applying the reshape function. So this gets reshaped. The test data is ready, and now the same code, friends. I did not change the code, but only the model got changed. I'll use this LSTM model on the test data where I'll get the predictions. Okay, so these predictions, as we have applied, you know, min-max scaling. So I'm just getting them undo. We are getting the scaling results undo. So using inverse underscore transform, we'll get the original values, and these values we are going to compare. Okay, the same code, but only the model got changed. But you see here how the results are. So these are the results that you have got using LSTM, long short-term memory RNN. So previously we have built an RNN model, but the end results are not up to the mark. No. So that makes a difference. So when you keep on trying, even though if you make some enough changes as part of, you know, as part of the architecture, even the results might be great. I hope it's making sense. So successfully we were able to predict, forecast Google stock price, okay, on a given day. Okay, so this is just a small use case where we have implemented RNN and LSTM. Okay, so in the upcoming programs, we'll make it bit complicated. We'll come up with, you know, some interesting programs will be conducted. And moreover, friends, from 16th of this month, April, we're going to launch a program on Python. It will be for 1 hour on daily basis, and we're going to start Python from scratch. Okay, where we cover core and advanced Python, including the basic libraries like NumPy and Pandas. Okay, so to complete your registration and be part of a wonderful program Python for AI, okay, and also share across your connections so that everyone will learn Python, right? So that's all for the day. Again, we'll meet in the next program. Until then, take care. Have a great day. Signing off.